Example 1 is calculate the mean ionic activity coefficient of 0.01 molal sodium chloride solution. Now here the molality is 0.01 mole per kilogram. Now when sodium chloride is dissolved in water, it dissociates as follows. It dissociates to produce positive sodium ions and negative chloride ions. When 0.01 molar dissociates, the concentration of sodium ion is 0.01 molar and the concentration of chloride ion is also 0.01 molar. Now ionic strength is equal to half of molality of sodium ion into charge of sodium ion square plus molality of chloride ion into charge of chloride ion square. Putting values, we get half 0.01 into plus 1 square. Plus 1 is the charge of sodium ion plus molality of chloride ion is 0.01 and charge of chloride ion is minus 1 square. Thus we get 1 by 2 0.01 into 0.01, yeah, half into 0.02. Ionic strength is equal to 0.01. Now the molality was 0.01, it was 1 electrolyte, therefore the ionic strength was equal to the concentration. Ionic strength is also equal to 0.01. Now according to Debye Huckle limiting law, log gamma plus minus is equal to minus 0.509 z plus z minus or into I under root. Putting the values, we get minus 0.509, 1 into 0.01, under root of square root of 0.01 is 0.1, therefore we get 0.509 into 0.1 is equal to 0.0509. Taking anti-log, we get gamma plus minus mean ionic activity coefficient is 0.889. Let us take the second example. We calculate the mean ionic activity coefficient of 0.01 molar magnesium sulfate solution. Here the molality is 0.01 mole per kilogram. Magnesium sulfate dissociates into magnesium plus 2 ions and sulfate minus 2 ions. The concentration of magnesium ion is 0.01 molar and the concentration of sulfate ion is 0.01 molar. Ionic strength is half of the concentration molality of magnesium ion into charge of magnesium ion square plus molality of sulfate ion into charge of sulfate ion square. Putting values, we get half into molality of magnesium ion is 0.01, molarity charge of magnesium is plus 2 square plus 0.01 into minus 2 square, or we get 1 by 2 half of 0.01 into 4 plus 0.01 into 4, half into plus 0.04 plus 0.04, we get half into 0.08 or 0.04. The ionic strength is 0.04. For an electrolyte producing two ions, both of which are divalent ions, when the molality is 0.01, the ionic strength is 4 times the molality, as we had already discussed. Now log gamma plus minus is equal to 0.509 z plus z minus into I. Putting the value of ionic strength and z plus z minus, positive ion has 2 charge, has 2 valency, and negative ion has also a valency of 2. Therefore we put the values and we get log gamma plus minus 0.4072. Taking anti-log, we get gamma plus minus is equal to 0.391. The third example is to calculate the mean ionic activity coefficient of 0.02 molar sodium chloride solution. We perform the calculation in the same fashion and we reach the result gamma plus minus is equal to 0.847. From these discussions, we can draw two conclusions. The first conclusion is, if we compare example 1 and example 2, the molality is same in both the cases, concentration is same, but the charges on the ions have increased. When the charges in case of sodium chloride, the charges are plus 1 and minus 1, and in case of magnesium sulfate solution, the charges are plus 2 and minus 2. When the charges on the ions increase, the ionic strength increases. For example, in case of 0.01 molar sodium chloride, ionic strength is 0.01, and in case of 0.01 molar magnesium sulfate, the ionic strength was 0.04. And when the ionic strength increases, the activity coefficient decreases. For example, for sodium chloride, the activity coefficient was 0.889, and for magnesium sulfate, the activity coefficient is 0.391. And when the activity coefficient decreases, then the active concentration will have a very large difference. from the actual concentration, and the solution will be more non-ideal. As the charges on the ions increase, the ionic strength also increases, the activity coefficient decrease, and the solution moves towards non-ideality. The second conclusion can be drawn by comparing example 1 with example 3. In example 1 and 3, we have used the same salt, that is sodium chloride, which produces +1 and -1 ions, but we have changed the concentration of the electrolyte. Now in example 1 we are using 0.01 molar sodium chloride, and example 2 we are using 0.02 molar sodium chloride solution. So when the molality or concentration of the solution is increased, the ionic strength also increases. For example, for 0.01 molar sodium chloride, the ionic strength is 0.01, and for 0.02 molar sodium chloride solution, the ionic strength is 0.02. And when the ionic strength increases, the activity coefficient decrease. For example, for 0.01 molar sodium chloride, mean ionic activity coefficient is 0.889, while for 0.02 molar sodium chloride, the mean ionic activity coefficient is 0.847. It has decreased. Thus, when the concentration of the solution is increased, the activity coefficient, the ionic strength also increases, and the activity coefficient decrease, and the solution moves towards non-ideality. Two conclusions which we have drawn show that as the ionic strength increases, the activity coefficient decrease, and the solution moves towards non-ideality. If we look at the mathematical form of Debye Huckle limiting law, we have the equation log plus minus is equal to minus 0.509 z plus z minus in under root of ionic strength. When the ionic strength increases, the activity coefficient decreases, and the solution becomes more non-ideal. Now, if we draw a graph between log of activity coefficient and ionic strength, we get the following diagram. Here we have the square root of ionic strength, and on y-axis we take log of plus minus. For 1 electrolyte like sodium chloride, we have this curve. We know that as charges on the ions increase, activity coefficient decreases. For a 2,1 electrolyte, we will have this graph. For example, calcium chloride. And for a 2,2 electrolyte, such as magnesium sulfate, we have this graph. Now in all these graphs, as the charges on the ions increase, the activity coefficient decreases, and the slope of these curves gives the value of Z plus and Z minus. The slope of each curve gives the value of Z plus and Z minus. Allah Hafiz.